We were considering transport, unidirectional transport in a cylindrical coordinate system in the last lecture. Okay. We had derived the balance equations by carrying out a shell balance over a cylindrical shell, okay, that is shown over here, of some height delta z and some annular differential volume between the radius r and the radius r plus delta r. Okay. So, these were cylindrical annulus differential volume of infinitesimal thickness, and for this we did a balance and we got the balance equations of this kind. Okay. This was the balance equation for the temperature, and if the thermal diffusivity, if the rho and Cp are constant, we got this one, and further if the temperature, if the diffusivity is independent of temperature, this is what we get. Okay. Note that the form of the differential is slightly more complicated than that for a Cartesian coordinate system, because the surfaces are curved. The surface area changes as the coordinate r changes, and because of that you get a slightly more complicated form of the differential operator. Similar we had got for the concentration equation, it is exactly the same. Substitute concentration for temperature, mass diffusivity for thermal diffusivity, and the mass source for energy source by rho Cp. And I told you that for an axial flow, where the flow is along the x direction, where x is the axial direction, the differential equation is identical to what we had for mass and energy. But if the flow is along the circumferential direction, the phi direction, then you get slightly more complicated form of the equation. Okay. So, this also we had seen in the last few lectures, and then we were proceeding to solve equations at steady state. Okay. The balance equation 1 over r d by dr of r times dt by dr is equal to 0 in a radial coordinate system. Simplest problem is the heat transfer in an annulus with inner radius Ri, outer radius Ro, temperature Ti inside, temperature To outside. We had to find what was the heat transfer rate in this case. Scale R by the radius of the inner cylinder and define a scale temperature such that it is 0 on the inner surface and 1 on the outer surface. In this way you can get an universal form for the differential equation, okay, and the boundary condition. The only thing that the boundary condition will depend upon is this ratio Ri, the ratio of the outer and inner radius. Unlike in the Cartesian coordinate system, where we could get both the equations and the boundary conditions to be completely parameter free. Okay. In this case we get the equation as parameter free, but the boundary condition just does depend upon this ratio Ro by Ri. Okay. So, one has to be careful about that. In cylindrical coordinate system, the ratio of the outer and inner radius is always a parameter in the problem. So, we had solved this equation, integrated it one time and got r times dt by dr is a constant, and dt by dr is equal to a over r. Okay. Integrate a second time and you get t is equal to a log r plus b. Based upon the non-dimensionalization that I have done, okay, b has to be 0 because t star is 0 on the inner surface, and a has to be 1 over the log of Ro by Ri. Okay. Note that the log has to always got to be taken of terms with equal dimension. Okay. So, this was the solution that I had got for the temperature field. The heat flux minus k times partial T by partial r. Okay. Express T in terms of T star, express R in terms of R star. The scale for T is the difference in temperature between the inner and the outer radius. The scale for R is the inner radius, okay, and therefore I get QR is equal to minus k times To minus Ti by Ri into log of Ro by Ri times R star. Okay. And R star times the inner radius is just the actual radius R, because I defined R star is equal to R by Ri. Okay. So, therefore, this is the expression for the heat flux in the R direction QR. Okay. Now, you can get the heat transfer rate at any radius r. Okay, the heat transfer rate at any radius r, okay, by multiplying, okay, the heat transfer rate q r. Okay. If I take a pipe whose length along the axial direction is L along the axial direction, okay, if I take a pipe of length L, okay, so that the length along the axial direction is equal to L, okay, then the heat transfer rate has to be equal to the surface area at the radius r, okay, 2 pi r L into q r. Okay. This has to be equal to minus 2 pi L into k into T naught minus T I by the logarithm of R O by R I. Okay. This is the heat transfer rate. Okay. Heat goes from higher temperature to lower temperature. Therefore, if T O is greater than T I, the heat flux is in the minus R direction inward. Whereas, if T I is greater than T O, then Q R is in the plus R direction outward. Okay. Note another thing here. Q R depends upon R, whereas the heat transfer rate does not depend upon the radius. Okay. At any surface within the cylinder, the heat transfer rate has to be the same. That is because there is no source or sink within the material. Okay. Therefore, the amount of heat that is coming in at one surface has to be equal to the amount of heat that is going out at the other surface. So, the heat transfer rate itself has to be independent of position. Okay. The heat transfer rate itself has to be independent of position. The flux is not independent of position because the surface area is changing. The product of the flux and the surface area has to be independent of position. The flux is proportional to 1 over r, surface area is proportional to r in such a way that the heat transfer rate is the same. So, this gives you the heat transfer rate. It is the same on the inner cylinder, inner surface, it is the same on the outer surface, and it is the same on any other surface within the fluid. Okay. So, the heat transfer rate has to be identically the same in all cases. Okay. This is the solution for the heat transfer rate. Okay. Sometimes an attempt is made to write this heat transfer rate in terms of an area and a thickness. Okay. Obviously, if you take the analogy with heat transfer in a plane surface, okay, you know that the Qz, okay, in the z direction is equal to k into T naught, k into the temperature difference into A by the thickness h, where h is the thickness of this plane, okay, differential volume in a Cartesian coordinate system. Okay. This is just Fourier's law for heat conduction, the heat flux times the area, and the heat flux is equal to minus K A delta T, okay, where A is the cross sectional area. Okay. A will be the cross sectional area. Okay. If you try to write it in a similar form, okay, what you would write is that QR is equal to minus K A L into T naught minus T I by the thickness, which in this case is R naught minus R I. Okay. Okay. This would be, if you write it this way, right, then this A L is not the actual area. Okay. it is called what is called the logarithmic area. Okay. So, if these two expressions, okay, if these two expressions have to be the same, okay, if you were to write it in this particular manner as the difference in temperature divided by thickness times an area, okay, for these two expressions to be the same, then the area has to be given by is equal to 2 pi k, sorry, 2 pi L, okay, into Rho minus Ri by the natural logarithm of Rho by Ra. Okay. That would be the expression for Al in such a way that if you substitute that expression for of Al into an expression for the heat transfer rate, which is similar to what you have in a Cartesian coordinate system, then this area has to be given by this, so that you get the correct result for the heat transfer rate. Okay. So, that you get the correct result for the heat transfer rate. Okay. And this is called the logarithmic area. Okay. This is called the logarithmic area. Okay. And the logarithmic mean radius is obtained by writing this is equal to 2 pi r okay. That is the area Al is equal to 2 pi times RL times L, which gives us an expression for the logarithmic radius as R0 minus Ri by ln of R0 by Ri. This is called the log mean radius. Okay. This comes from an attempt to force fit the expression that we actually get in a cylindrical coordinate system to what we would have got for a Cartesian coordinate system. Okay. It basically emerges from an attempt to force fit the expression, okay, by defining an area, so that if you define the area this way, in the end you get the correct expression for the heat transfer rate. Okay. That you will get if you define the log mean radius in this manner and the thickness as R0 minus Ri, Rho minus Ri. Okay. So, but we shall not use this in this present course. We will directly use this expression, okay, for the total heat transfer rate, okay, rather than using this expression in terms of the log mean radius. Okay. So, what we have got so far, Qr is equal to minus 2 pi L k into T naught minus Ti by ln of R0 by. Okay. You can verify that this has the correct dimensions. K has dimensions of watts per meter per degree centigrade, okay, which implies that Qr has dimensions of watt. Okay. Okay. As it should be, okay, because Qr is an energy transfer rate, energy transferred per unit time. So, K multiplied by temperature multiplied by distance L. In the denominator, the log function is dimensionless. Okay. In the denominator, the log function is dimensionless. So, we get the correct dimensions. Okay. Okay. What if we had instead of one cylinder, we had two cylinders concentric. Okay. So, one of them was made of one material, the other was made of another material. Okay. Inner radius Ri, interface radius Rf, and outer radius is Ro. Okay. And I specify what is the temperature inside and the temperature outside, and I want to find out what is the heat flux. Okay. Given that the conductivity inside is Ki and the conductivity outside is Ko. Okay. Given these two conductivities, I would like to find out what is the heat transfer rate in this case, okay, between these two. If we assume temperature is equal to Ti, okay, so T is equal to Ti at R is equal to Ri and T is equal to To at R is equal to Ro. Okay. Now, how do we find the total heat transfer rate? In this particular case, the total heat transfer rate has to be the same for both materials, because there is no energy source or sink at the interface between these two materials. Therefore, the energy transfer rate has to be the same for these two materials. Okay. Assume T is equal to Tf at the interface. Okay. Assume T is equal to Tf at the interface at R is equal to Rf. Okay. Then we can write the expression Qr is equal to minus 2 pi k of the inner material times Tf minus Ti by ln of Rf by Ri for the inner material. Okay. Okay, for the inner material, this is the energy transfer rate. The flux is not independent of R, but the energy transfer rate is independent of R. Therefore, for the inner material, this is what is the energy transfer rate, and for the outer material, the energy transfer rate is 2 pi L Ko into To minus Tf, temperature difference between the outer surface and the surface at Rf, okay, by ln of Ro by Rf. Okay. In the first case, for the material with conductivity Ki, the inner surface has radius Ri and the outer surface has radius Rf. For the outer material with conductivity Ko, inner surface has temperature Tf, outer surface has temperature To, inner surface has radius Rf, outer surface has radius Ro. Therefore, I can get the temperature difference across both of these materials. Okay. Tf minus Ti is equal to minus Q log of Rf by Ri by 2 pi L Ki. Okay, this is Qr. Okay. I can also write this as minus Qr by 2 pi L Ki by log of Rf by Ri in the denominator. Okay. And the difference To minus Tf is equal to minus Qr by 2 pi L Ko by, my apologies, it should be a divided by. Okay. Okay. By log of Ro by Rf. Those are the two expressions. Okay. Just add these two up, okay, and you will get To minus Ti is equal to minus Qr into okay. Okay. This gives us an expression for the heat flux. Okay. Therefore, this just gives me that Qr is equal to To minus Ti into this whole thing inverse. Okay. Okay, this whole thing inverse. Okay. Recall that when we had solved the problem of conduction in a slab with two different kinds of materials K1, K2, H1, H2, right. We had written that the resistance R, okay, R1 is equal to T1 minus T naught by Q, okay, and that was given by H1 by Ka, okay, that was the heat transfer resistance, okay. So, T1 minus T naught by Q, okay, if T is this is equal to okay, let me just clarify this a little more. Okay. This T is equal to T naught, T equals T1 and T is equal to TH, okay, and okay. So, Qz in that case was equal to delta T divided by R, okay, is equal to delta T1 by the resistance for the first surface R1, okay, where R1 was equal to H1 by K1A, okay, was the heat transfer resistance. Okay. This was also equal to delta T2 by R2. Okay. Delta T2 is the temperature difference across the slab of thickness H2 with conductivity K2, and delta T1 was the temperature difference across the slab with thickness H1 with conductivity K1, and I have to be consistent here. So, I will take this as H1 and H2, and the temperature difference here will be delta T1 and delta T2. Okay. So, in a similar manner, I can also solve for a cylindrical coordinate system using a similar framework. Okay. I can define the resistance in this case. Okay. I can define the resistance in this case as the resistance of the let me call it as resistance of the inner cylinder. Okay. The resistance of the inner cylinder is equal to delta T across the inner cylinder divided by QR. Okay. Okay. So, delta T by QR will be equal to log natural log of RF by RI by 2 pi L Ki. Okay. Okay. And the resistance of the outer cylinder will be equal to delta TO by QR is equal to the natural log of RO by RF by 2 pi L K O. Okay. So, these are the two resistances. Okay. So, this is the resistance of the inner cylinder, this is the resistance of the outer cylinder. Okay. Therefore, QR will be equal to TO minus TI into the resistance of the inner cylinder plus the resistance of the outer cylinder with a negative sign here. Okay. So, these resistances are all defined with negative signs. Okay. So, this is equal to okay. So, for a series arrangement of resistances, you have to add up the resistance. Okay. The total resistance is the sum of the two resistances. Okay. Similarly, if you had multiple annular layers of different thicknesses all you have to do to find out the total flux is to add up all of the resistances. Each resistance, which is equal to delta T by Q, which is log of the ratios of the outer and inner cylinders divided by 2 pi L times the conductivity. Okay. Okay. So, this is the analog of the resistance formulation for heat transfer in a cylindrical coordinate system. In a Cartesian coordinate system, the resistance was proportional to h, the thickness, inversely proportional to area. In this case, you are getting the logarithmic, not natural logarithm of Rf by Ri, and it is inversely proportional to the length and the thermal conductivity. Okay. So, that is the expression for the resistance, and in a series arrangement you will add up the resistances. In a parallel arrangement, for example, okay, a parallel arrangement would, for example, correspond to different zones, okay, having different materials, okay, different zones having different materials. In that you would add up the inverse of the resistances. Okay. So, in a parallel arrangement you would add up the inverse of the resistances. In a series arrangement like the one that we have here, where you have two annular regions in series, you would add up the two resistances, and the heat transfer rate will be equal to the temperature difference with a negative sign, because it is proportional to the difference, it goes from higher temperature to lower temperature. So, you will have the temperature difference with a negative sign multiplied by the sum of the resistances. Each resistance is the log of the outer and inner radius divided by 2 pi L times the thermal conductivity. Okay. So, that is the expression for the heat transfer in a cylindrical coordinate system. Okay. You can use exactly the same formulation as we had for a Cartesian coordinate system, except that the resistances now have to be defined based upon the natural logarithm of the outer and inner radius. It is not just equal to the ratio of the thickness, it is not just equal to the ratio of the thickness and the area. Okay. Okay. It has the same dimension, 1 over length times 1 over conductivity, but it is slightly more complicated because it is in a cylindrical coordinate system. So, let us look at an example. Okay. I have a flask, vacuum flask. Okay. So, in a vacuum flask usually you have a region which is evacuated, which contains no air, and because when there is no air the thermal conductivity is very small, therefore, it retains heat for a long time. Okay. So, a vacuum flask with inner diameter 4 centimeters and outer diameter 4.2 centimeters. Okay. And the height is equal to 10 centimeters, Ri is equal to let me be a little careful here. This is not the radius, okay, it does not make a difference to the calculation of course, but formally the inner diameter is equal to 4 centimeters, the outer diameter is equal to 4.2 centimeters, height is 10 centimeters, filled with water, okay, of density 10 power 3 kg per meter cubed, specific heat 4.2 into 10 power 3 joules per kg per degree centigrade. Okay. The outside temperature T0 is equal to 25 degrees centigrade. The temperature inside initially, okay, Ti is equal to 100 degrees centigrade at T equals 0, okay, at initial time. And I have a conductivity for the vacuum flask. Okay. The conductivity K is equal to 2.4 into 10 power minus 3 watts per meter per degree centigrade. And what I want to know is the time taken for temperature to decrease to 50 degrees centigrade, assuming that the temperature of the water is uniform and all of the heat transfer resistance is due to the vacuum zone between the inner and outer cylinders. How long does it take for the temperature to decrease, and based upon that I can decide how long the flask will be useful. So, this problem, practical problem of conduction in a cylindrical coordinate system, I will continue in the next lecture. We will find out the time taken to reduce the temperature to 50 degrees centigrade from 100 degrees centigrade. I will continue this discussion in the next lecture. I will see you then.